We only saw each other one time this week, so I wanted to make sure that I recap what was covered in class on Tuesday, either for those that missed it or those that wanted to see it again. So just a reminder, next week when we take our exam, there are basically going to be 5 types of questions that you might encounter, and I've kind of indicated here on this outline where you can see some practice problems. So we only had 2 homework assignments this unit. That was homework 8 and 9 in Math Excel. So if you're looking at my notes that say number 1, that's really referencing homework number 8, and number 2 references homework number 9. So I'll ask you to find general solutions to differential equations. I'll ask you to find solutions to separable differential equations. So those are a little bit more complicated than the initial general solutions that we had. A lot of times we'll give you initial values there as well when working on problems like number 2. There'll be some questions on slope fields and word problems, and the Math Excel word problems I think are a pretty good description of what you'll see. But also the other video that I've recorded, I talked about some word problems there as well, some exponential growth and decay problems. Those are good. And then I do think I am going to ask a question about an equilibrium state, and I've got 1 or 2 in this video that can help describe that. So here we go. And then you know what? I might even break this up into a couple videos if needed, if this starts to get a little bit long. So here we go. Question on our slope fields. Here we have a slope field that was generated for us. And I just wanted to reiterate the fact that the slope field shows all possible solutions to a differential equation. It's kind of like that family of functions that we've seen because of that C value. This question simply asks us to sketch a graph of what the original function y would look like based on the differential equation or the slope field that's shown here. So if we were to look at number 1, well, if we have an x value of 0 and a y value of 1, that's a coordinate that lands right here. If this coordinate is on our function y, and the shape of y is determined by the slope field, then we might say or might see that the original function y might take on this shape here. So I'm not looking at you all being perfect artists here, but indicating that this would be the shape of the original function. I think that's pretty reasonable. Now in number 2, if our y value is 2 when x is 0, now we're up a little bit higher here, and we start to see this behavior. We're starting to see this steady state present itself. We can see that right here horizontally. The shape of this function is different than the shape of the red function. So in this case, based on the 2 different initial conditions, we actually have 2 different y equations that still satisfy the same differential equation. Number 3, that gets kind of interesting when x is 0, y is pi. So I think that's this spot right here. And wouldn't you know it, that's the equilibrium point. That's the steady state solution, if you will. If our initial condition was pi, well then the shape of the function remains constant. It's flat throughout. So that's kind of an interesting result. If we were to look at question 4, well, now we're up here, or part 4, I should say, now we're up here, and the function actually decreases towards this level position, this constant value. And then finally, on number 5, if we had a y value of 5 when x was 0, then that function tends to level off to this shape. So 4 different solutions that all are represented by the exact same differential. So that's kind of nice. And we'll go ahead and skip B for right now. I'll revisit that if I feel like it's important. Let's talk about number 6, this example number 6. This is an interesting question that involves differentials, and it's kind of an interesting setup to the problem as well. We're told that a tank contains 20 kilograms of salt dissolved in 5,000 liters of water. So we're not talking about like an army tank. We're talking about like a collection tank, some giant cylinder out in the field or something like that. Contains 20 kilograms of salt that's been dissolved in 5,000 liters of water. So we have a saltwater solution of sorts. in this tank. Brine, another saltwater solution that contains 0.03 kilograms of salt per liter, enters the tank. So we're pouring in this brine solution at a rate of 25 liters per minute, and the solution inside the tank is kept thoroughly mixed. So we're going to constantly mix this up with this new solution as it pours into the existing solution. And we're going to maintain the 5,000 liters because as we fill up the tank with 25 liters per minute, we're also letting it drain out at 25 liters per minute. The question becomes how much salt remains in the tank after half of an hour. Now, this is a particularly interesting question because even though we're talking about mixtures and solutions here, the question itself is asking how much salt in kilograms remains in the tank after half of an hour. And then since our unit of time here is minutes, I'm going to indicate that half of an hour is not 0.5 hours, but we'll use the number 30 minutes. All right, so with a little bit of focus, I think we can start setting this up. So I'm going to say that S stands for the amount of salt in kilograms. And I'm going to let T represent our time in minutes. And so the function S of T, that's the equation that describes how much salt is in the tank in kilograms after a certain amount of time. So if S of T represents the amount of salt, then ds dt, the change in salt with respect to time, is the rate of change of the salt mixture in the tank. So that's the rate at which the salt mix is changing in the tank. By the way, if I took 20 kilograms and divided it by 5,000, 20 kilograms divided by 5,000, that'll give me my mixture rate in kilograms per liter, and we could compare that number to the 0.03. So I got curious about that. 20 kilograms dissolved in 5,000 liters is a concentration of 0.004 kilograms per liter. So that tells me that this is a much saltier mix. We're going to increase the amount of salt within the tank as time progresses. Okay. Now, I also want to point out here before we start to do any additional math is that this ds dt, the rate of change of the salt mixture within the tank, will be equal to the rate of the salt as it's being poured in, or rate of salt input, we'll say, minus the rate of the salt output. So at what rate is the salt mixture coming in, and at what rate is the salt mixture going back out? And this is the hard part. This is the hard part to recognize. So I'm going to give this as a hint to you on the test to remember that we should take the rate of input and subtract the rate of output. But it's up to you to figure out how to set up the equation from there. So I'm going to note that this rate of salt input, now the units that we're using here is a kilogram per minute. Right, that's what our ds dt represents. But if we look at what was given to us up here, we know that we had a 0.03 kilogram per liter quantity. That's going into the mix. And we have 25 liters per minute at a rate of volume. So we have 25 liters per minute of the volume going in. Well, as it turns out, the product of these two, the kilograms per liter mixture times the 25 liters per minute volume, that allows us to cancel some terms here. The product of those two numbers generates a unit of kilograms per minute. So that's great. So this ds dt, at least for the input quantity, is whatever 0.03 times 25 is. That math's not too hard, so we'll go ahead and do this. 0.075 kilograms per minute. And that's great because now I can see that this unit can potentially produce the kilograms per minute unit that we were after on the left side. Now, to be careful though, oops, sorry, this is subtraction. The only way that we can combine two units to make the same thing is if they are the same themselves. So this expression over here, the rate of salt output, also needs to be in kilograms per minute. So I wonder if we can set up an expression the same way here too. Now, what's going out is an unknown amount of salt mass per liter. So this is the unknown, and this is what's going to be changing as time progresses. So the amount of salt in the tank over a quantity of water in the tank or a mixture in the tank. All right, so this is going to be a kilogram per liter measurement. That could be multiplied by the same 25 liters per minute that's exiting the tank, because as 25 liters per minute is being flowed into the tank, 25 liters per minute is being pushed out of the tank. So those two numbers are the same. We were told that. Now, if the problem was a little bit more challenging and we said that we were draining or pumping out at a different rate, then we could make that adjustment. But in this case, we were told that the amount coming in terms of volume is exactly the same as the amount going out in terms of volume. So the product here does produce our kilogram per minute unit. So kilogram per minute is the result here. This number of kilograms per minute and this number of kilograms per minute are allowed to be subtracted. Those two units agree, and then ultimately they do create the kilogram per minute unit that we have on this outside. So I'm borrowing some of the techniques from our physics class, just doing some dimensional analysis real quickly here to make sure that our equation itself is meaningful. Now I just checked off to the side, 25 times 1 over 5,000, or 25 divided by 5,000 turns into 1 over 200. So I'm going to rewrite this as 1 over, 200, not 1,200, 1 over 200 times S, or S of t. So now whatever 1/200th of the existing salt mass is, that's going to be a component of our differential equation. So one more time to make the math a little bit clearer, I'm going to rewrite this function without my notes and without my units, and I'll just note that 0.75 minus 1/200th S is the differential equation that we need now to solve. So we've been focusing on separable differential equations in this class, and you may recall that separating these can be a little bit tricky. We can't just move this term to the left and leave 0.75 on the right, because in the act of integrating after that, we won't get the units that we're after here. Terms that are separated by this addition or subtraction sign as we move this differential over gets to be a little bit more complicated. So what I'd really like to see is, instead of a sum or difference of terms, I'd like to see a product of two numbers. So I'm going to note that ds dt is equal to, I'm going to treat this 0.75 like a GCF. If I factor out a 0.75, or actually no, I take that back. Let's isolate the s. Let's use the 1/200th as our GCF. Let's do that. Let's do it this way. If I divide both of these by 1/200th, then the coefficient 1/200th gets pushed outside of a fraction, and 0.75 divided by 1/200th, or in other words 0.75 times 200, that works out nice. That's 150. And by factoring out this 1/200th, I'm now left with 150 minus S. Here's where the separation of variables can occur. Now I can divide this expression that contains S to the left side. Now I can multiply this dt to the right side, and we have a separated differential equation. 150 minus S, underneath 1 of course, ds, is equal to 1/200th dt. And if we integrate both sides of the equation, we've seen this procedure many times before now, we get the natural log of 150 minus S. I have to introduce a negative sign here to combat the negative sign in here. It's kind of like a mini chain rule. You could use a U substitution there to calculate that as well, but that's what we've got, plus C. But the C value from this side, I'm going to immediately push over to the right side. And now the antiderivative of 1/200th is, with respect to t, is 1/200th t, and then that new C value combined from the left and the right. Okay, so now we're off to the races. Now it becomes an algebra problem. First off, I'll divide both sides by 1, so that changes our sign over here. Technically, this becomes minus C, but again, C is just some constant that we don't know the value to yet, so we're just going to keep calling it C along the way. I will use the base of e raised to this exponent to eliminate my natural log. So now we have 150 minus s is equal to c times e to the negative 1 over 200t. That looks pretty good. And then if we're trying to get s by itself, then s would be equal to 150 minus c e to the negative 1 over 200th t. All right, so now we have a general solution to the problem. If we jump back up to the given info, we know that there was 20 kilograms of salt at the beginning of this event at time 0. So to solve for our C, our initial condition, we can set 20 equal to S, and now 150 minus C times e to the negative 1 over 200 times 0. Well, this group turns into a 1 because e to a power of 0 is 1. So that goes away. 150 minus c has to equal 20. So now we know that c is equal to 130. Cool. So our c value is 130. It looks like our solution in this case is solution to the differential, that is 150 minus 130 e to the negative 1/200th times t power. Okay, very good. Let's see what we have to do next. The solution is kept thoroughly mixed. How much salt remains in the tank after half of an hour? Well, we've got the initial conditions accounted for, so we have a starting point. If I want to find the amount of salt in the tank after half of an hour, keeping in mind that we did use minutes as our unit of time here, then we'll just change t to 30. And then evaluate this expression. And so the calculator off the screen has shown me 39.1080 when rounded to 4 places. Sorry, that's 38.1080, and that's measuring the mass of the salt, kilograms, inside the tank. Now, this answer does make a little bit of sense to me. I'm not 100% sure if it's numerically correct, but it seems reasonable. The 38 is larger than 20, and as we said at the beginning here, the saltwater mix that we're pouring into the tank is a higher concentrate than what was in the tank originally. So I think this is pretty good. I think that's a fine answer to the question. I almost said solution. No pun intended. I think I'll stop the video here and I'll record another 1 or 2 separate while we talk about the remaining word problems. Thanks for watching.